So section 11.2, we're going to be talking about different geometric figures here, guys. And it says, with a pencil, draw a path on a piece of paper without lifting the pencil and without retracing any part on the path except single points. The resulting drawing is restricted to the plane of paper, and not lifting the pencil implies there are no breaks in the drawing. The drawing is connected and there's a curve. It says Table 6 shows sample curves and their classifications. A check is placed in a box if the curve has the attribute listed at the top. Okay, so before we look at what is simple, what's closed, polygon, convex, concave, let's at least look at some of those definitions, and I have them right here. Okay, so first off, simple curve. Simple curve, number one, does not cross itself. And starting points and stopping points may be the same. A closed curve is one that starts and stops at the same point. So that would be a closed curve, right? And a polygon is a simple closed curve with sides that are line segments, okay? And then we also have something called convex and concave. So a convex curve says it's simple, so it doesn't cross itself. It's a closed curve with no indentations. The segment connecting any 2 points in the interior of the curve is wholly contained in the interior. And a concave curve is simple, it's closed, that is not convex. And notice what it says. It has an indentation. Okay? So let's take a look at some of these things here just so that we have an idea of what this is, right? So you can see almost all of them are simple curves with the exception of, come on, pen, here we go. This one right here, right? Because the first column is simple curves. So let's see, why is this one here not simple? Because a simple curve, what? Does not cross itself. And you can see this one here crosses itself, right? Okay. Why are these two not closed? Because you can see that they're not like connected at the ends, right? Where all of these are. Okay. Polygon says that the connecting parts are going to be line segments. So these are like my line segments right here, these two. This one isn't because it has that little curve right there, right? Convex and concave. So remember, let's go back and look at convex and concave. Concave says it has an indentation, okay? It has an indentation. So if you notice, like right here, here's my indentation, and then I guess this part here would be my indentation, or right here would be my indentation, right? So that's what they mean by those things, okay? Okay, so now let's talk a little bit about triangles. So a triangle is contains one right angle. It's called a right triangle. A triangle in which all the angles are acute is called an acute triangle. You're so cute. A triangle containing one obtuse angle is an obtuse triangle, okay? Obtuse, guys, just means that the angle is going to be bigger than 90 and smaller than 180. So my angle here, say we call this angle X. X is going to be between 90 and 180 degrees, okay? And then it says a triangle with no congruent sides is what we call a scalene triangle. So none of the sides are going to be having the same measure, okay? No sides will have the same measure. That triangle will be called scalene. All right, and it says a triangle with at least 2 congruent sides is an isosceles. And a triangle with 3 congruent sides is an equilateral. Guys, equilateral triangles are also equiangular. Those angles are also going to be the same, okay? So let's see, what else do we have? A trapezoid is a quadrilateral with at least one pair of parallel sides. So this side here and this side here are parallel, okay? A kite is a quadrilateral with 2 sides being congruent, 2 adjacent sides being congruent. So these are my adjacent sides. They meet right there. And these are my adjacent sides. They meet right there. And you can see those are congruent, okay? An isosceles trapezoid is a trapezoid with congruent base angles. Okay, we got the picture right here. This angle here and that angle there have the same measure. A parallelogram is a quadrilateral with each pair of opposite sides are parallel. So these are parallel here, and those are parallel there. They also have those sides, are also going to be congruent, meaning they're going to have the same measure. Okay, that's all congruent means. A rectangle is a parallelogram with a right angle. A rhombus is a parallelogram with two adjacent sides congruent, and a square is a rectangle with two adjacent sides congruent. Okay, so let's see if we can go through some of these questions. And a big part of it, guys, I'm going to kind of be scrolling back and forth just so that I can use my definitions. It says, if possible, draw a right scalene triangle. If not possible, state why. Okay, so let's see. We know what a right triangle looks like. A right triangle says it has a right angle right there. That's a right triangle. Scalene says the sides are all going to be different. Okay, so we want it to have a right angle, and we want all the sides to be different. So this is 8, this is 6. That number there will not be 6 or 8. There's my right scalene triangle, right? So number 1, it had to be a right triangle. So that's why I knew it was an A or B. Okay. All right, draw an obtuse scalene triangle. Okay, so remember, scalene, sides are going to be different. Obtuse, the main angle is going to be bigger than 90, smaller than 180. Boom, there we go, right? This angle here, bigger than 90, smaller than 180. All my sides are going to be different, okay? Draw an obtuse equilateral triangle, okay? Obtuse. So remember what obtuse means. If I come back over here, where is obtuse? Obtuse, obtuse, here we go. Obtuse means the angle is going to be greater than 90, smaller than 180, right? Greater than 90, smaller than 180. And it needs to be equilateral. So remember what we said about equilateral. Equilateral triangles look like this. And like say this is 5, this is 5, this is 5. But those angles all measure the same. And those angles are actually 60 degrees. So this one here, guys, it's not possible. Because an equilateral triangle has 3 60-degree angles, okay? All right, so now let's talk a little about symmetry and its relation to planar figures. So paper folding can be used to introduce the concept of symmetry. So again, if you were to kind of take this picture here, and if you were to fold it along this side, you would see that, you know, this side here and that side there would match up. You can fold this one here. You can fold this one in many places, and this one you can only fold it once, right? Straight down the middle. That's what we talk about lines of symmetry, okay? So this next one here says, how many lines of symmetry does each drawing in figure 23 have? This is our figure 23. Okay, so look, we could fold it right there. That's one line. We could go right here. That's 2 lines. We can go right here. That's 3 lines. Couldn't we also go on our endpoints? 4, 5, and 6. 5 and 6. So this one has 6, okay? All right, if I were to do this one here, I believe this one here is only going to have 1, right? Fold it down the middle, it's going to have 1. This one here should have 2, once right here, and once right there, so it's going to have 2. This one's not going to have any, right? No matter how I cut it, it's not going to work. That's not going to be the same if I cut it in half, right? If I fold it along that line. If I were to fold it along this line, would it look the same? No, because, yeah, this one wouldn't be the same either. So this one has 0. Okay. All right, we have something called, rotational or turn symmetries. And it says a figure has a rotational symmetry or turn symmetry when the trace figure can be rotated less than 360 about some point. The turn center so that it matches the original figure. So we notice from here they go 120, they go another, they go 120, another 120, another 120, so on and so forth, right? Okay, so it says determine the amount of turn for the rotational symmetries of each figure. All right, so we're going to go look. We can rotate this point to this one, so on and so forth, okay? So the way I can do this is I can say, look, remember, when I have a complete circle, it's 360, right? How many endpoints do we have? We have 5. So let me grab my calculator, right? I'm going to move it over here for a little bit, turn it on. If I take 360 and I divide it by 5, okay, that's giving me 72 degrees, okay? But guys, I have to keep adding that same number until I get to 360, okay? So look, I'm going to add 72 again. 144 would be the next one, okay? And I'm going to explain why I'm doing this right now. Let me just keep doing this little trick here. 72, 216. Okay. Calculator, plus 72 again. 288. Okay. And one more time, plus 72. We go back to 360. Okay. So what I mean by that is when we rotate from here to here, that was a 72-degree angle. But if I decide I want to make this point here go over here, then we would have rotated it to 144. And suppose I wanted this point here to go all the way to that one, that would have been 216. And if I wanted this point here to go all the way to that one, that would have been that 288, right? And if I did it again, I would have ended right back to where we started off with, okay? So let's do the same thing here. If you notice, all my points, this thing is pretty symmetric, right? Very uniform. So again, I'm going to take 360. I'm going to divide it by 1, 2, 3, 4, 5, 6, 6, right? That's going to be 60 degrees. And then, so we're going to say, look, if we go from here to here, that's 60. What happens if we wanted it to go this way? That would have been 120. What happens if we wanted that point to go over there? That would have been 180. What happens if I wanted that point to go this way? That would have been 240. And what happens if I would have wanted it to go over here? That would have been 300, right? And these are all degrees because I'm adding 60 each time. Okay. All right. So from this one here, guys, what I would do is I would say, look, this point here could match up over there, right? So if I were to do this and do that rotation, 360, one way I can think about this, guys, is I have like two distinct points, like they're different. So I'm doing 360 divided by 2. That'd basically be 180, okay? And then I can't, if I add another 180, so that's 180. If I go back again, I'm right back to where I started from, okay? Alrighty, so let me scroll. All right, and it says any figure that has a rotational symmetry 180 is said to have point symmetry about the term center. Okay, so we have point symmetry about that point right there at the turn center, okay? All right, it says determine if the figure to the right has line symmetry, rotational symmetry, and or point symmetry. Okay, so I would definitely say this one has line symmetry, right? Line symmetry there. Doesn't look like it's going to have rotational symmetry. All right. This one here, also, I would say this is going to have line symmetry right about there. This next one here, also line symmetry right there. Okay. This one here, I would definitely say we're going to have line symmetry right there. And let's see. This one here would also have line symmetry right here. Okay. So it looks like all of these are going to have line symmetry. Okay. And was that the, oh yeah, we got one more up here. There we go. Line symmetry right there. So guys, notice this one here. If I were to rotate this, say here, 180 degrees, that would be rotational symmetry, correct? And anything that has rotational symmetry of 180 is also going to have point symmetry. So that one actually has all three. Okay. All right, so here's another one here. It says complete the sketch of the figure so that it has line symmetry about the line M. Okay, so if you look at problem A right here, all we're doing is we're saying, look, do this, do that. There's my A, right? This one's saying extend this way, extend this way. This piece here, extend it over there. That piece there, extend it over there. So B would be that one right there. Okay. All right, diagonals in a polygon. It says the number of diagonals in an n-sided polygon is given by this formula. Okay, so the first part says determine how many diagonals each of the following has. Okay, so let's do part A. Part A says a heptagon. Okay, so guys, in case you're wondering, heptagon's going to have 7 sides. So what I'm going to do is I'm going to take this formula right here, number of diagonals, and where I have my number n, I'm going to use the number 7. So I'm going to go 7 minus 3 over 2. This is 7. 7 minus 3, coordinate order of operations, is 4 divided by 2. 7 times 4 is 28. 28 divided by 2 is 14. So that's going to have 14 diagonals, okay? Let's do part B. Part B says a 20gon. So a 20gon obviously has 20 sides. So I'm going to take 20 minus 3 all over 2. Okay. So 20 goes in, or 2 goes into 20, I'm sorry, 10 times. 20 minus 3 is 17. And that's going to be 170 diagonals. That's a lot of diagonals, right? And then part C is asking us for a 13gon. So that's 13 sides, okay? So the number of diagonals is going to be 13 times 13 minus 3, all divided by 2. So that's 13. 13 minus 3 is 10 divided by 2. 2 goes into 10 5 times. And 13 times 5 should be 65. Okay. Here's my number of diagonals. Okay. All right. Same type problem. It says determine the number of diagonals. So my diagonals formula is n minus 3 over 2. Okay. So a nonagon has 9 sides. Okay. So I'm going to say number of diagonals is going to be 9. 9 minus 3 over 2. So this is 9. Let's see. 9 minus 3 is 6 over 2. 2 goes into 6 3 times. 9 times 3 is 27. Okay. All right, part B says 17gon. So that just means that there are 17 sides. So 17 minus 3 over 2. Okay. So 17 minus 3 is 14 over 2. 2 goes into 14 7 times. And I'm going to take my calculator here, guys, because off the top of my head, I don't know what 17 times 7 is. But we can figure it out. 119. Okay. And part C, number says 20gon. That's 20 sides. Did we do that earlier? Did we do 20gon? Yes, we did. We did it right here. And we came up with 170, right? So we don't got to do it again. We already know the answer is 170. Okay. All right. Determine the measures of the angles of a turn symmetry for each of the given figures. Okay. So guys, in order for me to rotate from this point here to this point here, again, notice this is like a parallelogram, right? But the points are not exactly the same. I mean, it's not uniform like the way this one is, right? So because I have 2 distinct points, I'm going to take 360 and I'm going to divide it by 2, and that will give me 180, right? Now, because when I rotate this one from here to here, or I rotate it from here to here, or I rotate it from there to there, it's all going to be the same. I'm going to take 360, I'm going to divide it by 4. It's going to give me 90 degrees, right? So that's just telling me that's how much I have to rotate it to go that way. If I wanted to rotate it to go this way, I would add another 90, give me 180. And if I wanted to do it one more time, I'd add another 90, and I'd come up with 270. Okay. And the same thing for this next problem here. So again, because my points are distinct, I'm going to take 360 divided by 2. That's going to give me 180. That means I'm rotating this point here. Let me see. All the way over here, right? Or this point here, all the way over there. Okay. This one here, again, because my points are the same, I can take 360 divided by 4. That's 90. That's rotating it there. Another 90 would be rotating it here. And another 90 would be rotating it there. And those are my angles, right? Okay, and that was 11.2.